here are the answers to the assessment on intermolecular forces. Question 1 asked about dispersion forces. That's when the electrons are not dispersed equally around the nucleus. It's a temporary, unequal distribution of electrons around the nucleus of an atom. Electrons are always moving and their movement is random. Most of the time they're equally distributed because like charges repel, but if by their random movement they're close to each other for a moment in time, you'll create a temporary charge. Question 2 gave you a table of liquids and their normal boiling points. It asked which liquid had the strongest intermolecular forces, which means the particles are most attracted to each other. Well, if they're the most attracted to each other, we should see the highest boiling point or melting point if it was a solid. So it should be the HF. You could also kind of look at these and find that the HF should be the one with the stronger hydrogen bonds. And maybe you kind of sketched out the structures. The other ones are all polar molecules, but none of them would have hydrogen directly bonded to an F or N like they are in the HF molecule. Oh, let's see here. Whoa, too far. Question 3. Solid iodine melts at 113 degrees Celsius. Which of the following best describes the melting point of solid astatine? And so these guys would both be diatomic solids. So normally iodine exists as I2 and astatine is A2. They are nonpolar when it's the same element bonded to himself. The nonpolar molecules really only have those weak dispersion forces, but the strength of the dispersion force can change depending on the number of electrons. So as I have more and more electrons, it's just more likely that they would not be evenly distributed around a nucleus. When you have 85 electrons, it's highly unlikely that at all times those 85 electrons are perfectly distributed, evenly distributed from each other. And so we're looking at option 1. The dispersion forces should be stronger, which means that the particles are more attracted to each other, and then we should have a higher melting point, something above 113 degrees Celsius. More total electrons, greater dispersion forces. Then you would have had one of either of these two, but not both, where they asked you to categorize the molecules based on their intermolecular forces. So sometimes it helps to sketch them, and maybe these are molecules that you're kind of familiar with now. They're, for the most part, things that we've already drawn to some extent. And so that may help. I did sketch out all of my little dot structures. Dispersion forces are for nonpolar molecules. So it could be like the nitrogen gas or the chlorine gas, where it's the same element bonded to itself. Or it could be like a perfect tetrahedron or linear, or it could be the perfect trigonal planar. I have 3 electron groups and they're 120 degrees apart. So I could have polar bonds arranged equally around the center, giving me a nonpolar molecule like methane or carbon dioxide. All the other ones ended up being polar molecules. So the difference between a dipole force and a hydrogen bond is that the hydrogen bonds are between molecules that have hydrogen directly bonded to FON. These are all going to be polar molecules with regions of charge, but because the FON have really extreme electronegativities and hydrogen only has 1 electron, those partial positive and partial negative regions are just a little bit more amped up in a hydrogen bond versus a dipole force, a little more extreme. So the HI and the HBr were both polar. I had phosphorus trihydride was polar because it had a 4th electron group. It was kind of like a tetrahedron, but I'm missing one of the spots. Same thing with similar, I should say, to the chloromethane. It's like a tetrahedron, but I don't have equal poles around my central atom. But in hydrogen bromide, chloromethane, hydrogen iodide, and phosphorus trihydride, I never have a hydrogen directly bonded to FON, like I would with the HF, the water, the ammonia, and the water. All four of those, again, are polar molecules with hydrogen directly bonded to FO or N. Then we went on to identifying hydrogen bonds. The key is that even though it's called a hydrogen bond, it's an intermolecular force. It's an attractive force between molecules where there is a hydrogen directly bonded to an FON, which just means that these partial positive and partial negative charges are really extreme, that the oxygen is really partial negative, and the hydrogens are strongly partial positive. In between those molecules, then, I would have attraction, but it has to be between oppositely charged ends of the water molecules. And it's not option A, because again, that would be just like a polar covalent bond. A hydrogen bond is between the molecules. I thought the question with the ion and water molecules was absolutely adorable. We've got water molecules surrounding some kind of an unknown particle. Which of the following must be true? So when I look at the arrangement of these water molecules, I see that it's always the partial positive hydrogen end that's attracted to this unknown particle, which then must mean that my unknown particle is negative, because opposites would attract. So this must be some kind of a negative ion in the middle. That would be surrounded by water molecules with their partial positive ends in. All right, then we had a couple questions where you were writing a sentence or two. In your own words, explain why the oxygen end of a water molecule carries a partial negative charge. This is all about electronegativity. Either you had to say electronegativity or explain what higher electronegativity on oxygen would mean. That because oxygen has that higher electronegativity, he's pulling on the electrons that are shared between the oxygen and the hydrogen. So that electron pair, if it's being pulled closer to oxygen and electrons are negative, makes that oxygen region slightly negative. Something about electronegativity being higher for oxygen, and then maybe explaining what that would mean. And then the last three questions were about two solutions. I tried to kind of sketch them here. Both flasks had a layer of water on the bottom and a layer of an alkane on the top. And so alkanes are always non-polar molecules. Here we had the example of CH4. And even though they were both clear, colorless liquids, you could still kind of tell that they didn't mix with one another. They layered. And if I kind of sketched the structures to confirm it, yep, CH4 would be a non-polar tetrahedron. Water's polar, it's that bent structure. And so the rule of solubility is like dissolves like. Since water is polar, it'll only mix with other polar molecules. So not something non-polar like the CH4. Now some people went into a little more detail, saying that because the water molecules are very attracted to each other with their hydrogen bonds, they're more attracted to each other than they would be attracted to something that's non-polar. Something that's non-polar has no regions of charge, so it wouldn't mix with the polar water molecules. Something along those lines, but you really had to explain polarity. What does it mean that like dissolves like? And how do I know that like water wouldn't mix with something like CH4? That, oh, because water is polar and the CH4 is non-polar. Then we added some potassium permanganate, an ionic compound where potassium is a +1 ion and permanganate is a big polyatomic with a -1 charge. Why did the potassium permanganate dissolve in the water, but not the alkane CH4 layer? Explain in terms of the structure of the molecules. And so again, we're going back to the concept of like dissolves like. that because water is polar, it'll only mix with other things that are polar. Polar meaning that the particle has to have a charge, has to have a charged region, or like these ions, they're totally charged, that there's a total transfer of electrons. So when I've got positive and negative ions, they'll be very attracted to the partial positive and partial negative ends of a water molecule. Opposites attract. So in order to dissolve in water, you got to be polar. You got to mix with the water, which means that you've got to have charges, like a polar water molecule. But now we also tried iodine, I2, and the iodine dissolved in the alkane layer, the CH4 layer, and both times and they made like a kind of pretty purple solution, which is kind of crazy that the solutions end up being like really similar colors, but they're made with two very different solvents and solutes. But yeah, the iodine would dissolve in the CH4 because now they're both nonpolar. And with them both being nonpolar, neither particle has a significant region of charge. So then they're perfectly fine mixing with each other.